to the cloud. So yeah, you got the notations here. I'm sorry, notation. I guess that kind of works. But the little blurb here, to find the equation for a plane that contains a given point. So kind of similar to the idea of a line. You're going to have a fixed point, and we want to be perpendicular to a given vector. So whereas a line, you want to be parallel to a given vector, for a plane, we actually want to be perpendicular to a given vector. That vector that we're perpendicular to, we call that the normal vector. All right. So in Calc 1, you might remember coming up with the equation of a tangent line, but you might also remember coming up with the equation of a normal line. A normal line was just perpendicular to the tangent, right, at a particular point. All right. So it's kind of a lot of the same. You'll feel a little bit of a bit of familiarity here. All right. So we're going to use the fact that the displacement vector between the given point P and an arbitrary point Q in the plane must be perpendicular to N, which means that their dot product must be equal to 0, right? If two vectors are going to be perpendicular or orthogonal, then their dot product has to be equal to 0. All right, so we're letting N be equal to ABC. All right, that was given. So we would make a substitution here, ABC. Now PQ is going to be connecting just like it did in the case of writing the equation of a line. It's going to be the displacement vector connecting a fixed point, some arbitrary point on the curve that's known, or I'm sorry, on the plane that's known, and some arbitrary point that's unknown, right? So if I want PQ, vector PQ, I'd be finding the displacement between P and Q. So X minus X sub O, Y minus Y sub O, Z minus Z sub O. All right, which we would then dot against ABC. All right, so if we dot that against ABC, then what we end up with, or what we should end up with, is a result of 0 because they have to be orthogonal to one another. All right, so I could actually use a little distributive property for dot products to expand this out and get A multiplied by X minus X sub O plus B multiplied by Y minus Y sub O plus C multiplied by Z minus Z sub O. Result would be equal to 0. I could distribute then further AX minus AX sub O plus BY minus BY sub O plus CZ minus CZ sub O. Now, you see that we have some terms that involve just a plain old X and other terms that involve the X sub O. Right? Anything that, I'm sorry, X sub O, Y sub O, Z sub O, the sub O's. So any of those terms are particular values. What we want to have when we write the equation of a plane, the plane should be in the form of AX plus BY plus CZ equals D, where D, A, B, C, and D are some, either scalar multiples or just a constant. All right. So anything that has X, Y, and Z should be over on the left. Anything that doesn't should be over on the right. So I could rewrite this as AX plus BY plus CZ and add everything else to the other side, which is AX sub O plus BY sub O plus CZ sub O. All right. Now, what that's telling us is that if we want it to be in this form, the AX plus BY plus CZ equals D, then all of this stuff on the right-hand side really has to amount to to whatever that D value is. Okay. And that's all well and good. It's just another formula to remember. But if we want to make this formula into a process, and that's kind of generally where we want to live with this stuff, it's like, okay, there's a formula, but how can we make our lives easier? What we can do is we can take our vector ABC, which is our normal vector, dotted against a vector associated with XYZ, right? So on the left-hand side, we'd be looking at the normal vector N dotted against ABC. I'm sorry, XYZ. And on the right, the normal vector N dotted against X sub O, Y sub O, Z sub O. Which in turn, if we really go back to basics here, it would really be the same as saying, well, what was the X? The X was the Q. No, I'm sorry, I keep saying X. XYZ was the Q, but Q was represented as a point. So what I'm saying here is let's represent Q as a vector. So N dotted against Q would be equal to N dotted against P. If you follow that model, you could actually pretty easily come up with the equation of a plane. All right. Now, what's the actual rule, the official rule? This. But what's the most useful form? This, as you'll see in the next example. Let's see, we got someone in the chat here. Oh, okay, thank you, Mike. All right. So actually make that adjustment now. All right, so in number 6, find the equation of the plane containing the point, right? That's a fixed point. It's a known point, so that's our P. That's perpendicular to the vector 3, 3, 6. That's going to be our N. With Q, Q is always, vector Q is always going to be XYZ, right? It's an unknown point corresponding to an unknown vector, variable vector, right? So what I would be saying here is I have vector P, which would be 2, 2, 1. Vector N, that was given, but I'll rewrite it. 3, 3, 6. Vector Q, X, Y, Z. All right. So if we follow this relation here, one of these days I'll be able to time like the words that are coming out of my mouth with what the actions are on the screen. N dotted against Q is going to give you 3x plus 3y plus 3z. And N dotted against P would give you 3 times 2, 6, plus 3 times 2 again, 6, plus 6 times 1, 6. So 3x, oh, I'm sorry, that was supposed to be a 6z. The repetition, it got me. So anyway, this would simplify down to 3x plus 3y plus 6z is equal to 18. All right. Now, you could simplify if you want because we have constant multiple, well, a constant factor that can be pulled out and simplified. But you also kind of lose the scale factor, you know, so we don't really want to do that. Like, for example, I mean, just kind of consider a parabola, you know, just in 2 space. If you had a parabola, y equals 2x squared plus 2x plus 4. You know, all the coefficients are 2. When you set it equal to 0, you can factor out a 2. and cancel it, but you would never just factor out a 2 just for the hell of it, because you would change the width of the parabola, right? Even though it would have the same roots, you would change the look of the parabola. It may even change the orientation. So we don't want to do that for a plane unless we're actually solving for something, right? Now, in the case of sketching the plane, now a plane is infinite. So if I really wanted to sketch a plane, I mean, technically I could do something like this and be like, well, there's your plane, you know, the whole screen, it's infinite, you know, it goes off in every direction, right? But what we do is we just do a first octant cross section of that plane, right? So just cut off by that first octant. So the way we handle that is by finding the intercepts. So we find the X, Y, and Z intercepts, and that gets the job done. So X intercept, if I turn off my auto correct here, X intercept, Y intercept, why I put a dash for one and not another is beyond me. And Z intercept. All right. In order to be on the Z axis, your X and Y values have to be equal to 0. In order to be on the Y axis, your X and Z values have to be equal to 0. And in order to be on the Z axis, well, actually, I did the Z axis first. I think I even said it that way, but it's labeled X intercept. So in order to be on the Z axis, your X and Y value should be equal to 0. I wrote that in the wrong place. In order to be on the X axis, your Y and Z values need to be equal to 0. So basically everything other than the variable you're investigating needs to 0 out, right? Which is actually pretty easy when you think about it. When you're in the standard form for a plane, you're just looking at it and saying, okay, well, if I 0 out the Y and the Z, then these two pieces would go away and you'd just be left with 3x equals 18. All right, so that would be that. So you just kind of toss that other stuff on the side. Then for the Y-intercept, you would toss out the 3x, the 3x and the 6z and collapse it down because those are zeroing out. And then you would toss out the X and Y terms. No, I don't want to copy it. And you would just be left with the Z component, Z equals 18. And it's pretty easy to solve there. I mean, very easy. X equals 6, Y equals 6, Z equals 3. All right. With this whole mess over here being the key to understanding, like what just happened there. Like a pile of nonsense on the ground. Actually kind of a cool visual, so I don't really want to delete it. All right. So like kind of like you're literally discarding the pieces you don't want. So you know, I'm gonna do it.
Quick question. So that pile, we're not using it because Y and Z equals 0. So that whole pile is 0.
So that whole pile is all the discarded pieces from each version of the equation. So in the first version, we had the Y and Z components going to 0.
Right.
So I tossed, by substitution, I tossed the Y and Z components into the pile.
Okay.
All right, and the same thing happened for the other two.
Got it.
Question, quick question. How did you get 18? I'm trying to figure out how you got number 18.
From the 6 plus 6 plus 6?
Yeah.
Or how did I get the 6 plus 6 plus 6 to begin with?
Correct. How did you get that?
Okay, so when we dot the n against the vector p, we take the 3 multiplied by 2, that gives you the 6.
Okay.
3 multiplied by 2 gives you the 6. And the 6 multiplied by the 1 also gives you a 6.
Okay.
Add them together, that gives you the 18.
Okay, perfect. Thank you.
No problem. All right, so this is got a little cool visual here, so I'm kind of liking it now. a discard pile. So anyway, plotting is actually very easy because all I'm going to do is take 6 steps along, and I kind of cheated here. I made enough dots on the axes for this to work out nicely, but I'm just going to take 6 steps along the x-axis, 2, 3, 4, 5, 6. Oh, it's funny how that works. 6 steps along the y-axis, and 3 steps along the z-axis. Right, but you could probably glean from what we're talking about here the importance of some aspects of this and maybe the lack of importance of other aspects, because you can easily create the graph of a plane on GeoGebra. So it's like, well, why are we doing this? It's really just to kind of give you a sense of how you can pull certain aspects of a graph, especially of a plane. But also it's the building blocks of other 3-dimensional surfaces, how we can get certain aspects and kind of disregard everything else. Because in GeoGebra, you can restrict your domain for X, for Y, for Z, whatever you want. It's just sometimes more trouble than it's worth. Sometimes just doing the computations out by hand, and it takes it a little bit further and a little bit faster, right? So that's kind of really the purpose behind this, because I mean, just think about a test. If you've taken a look at the practice questions on Blackboard, you haven't seen any instance where I've asked you to hand draw anything. If anything related to a graph came up, it was all do it on Desmos and come up with the image and give me a share link. So that's all stuff to keep in mind. This is really just for the sake of kind of developing a good visual, because eventually we're going to have to do calculus to this stuff, which means finding minimum, maximum values, concavity, and things like that. So getting a good intuitive visual understanding, intuitive/visual understanding of this stuff is really, really important, right? So the next page, kind of, you look at it and say, okay, well, it's the same question, find the equation of the plane, but it doesn't look anything like over here. It's here, it gave you a point, and then it gave you a perpendicular vector. It gave you that normal vector, and here it's like, well, geez, where's the normal vector? They didn't give us any of that, right? That's what makes it challenging, because now we got to incorporate multiple concepts, right? So I'm going to draw. I just learned that my app does this. I didn't even know that it like auto fixes onto a line segment if I just long press. I'm learning. So we know that if we're given 2 vectors, that we could find a third vector that's orthogonal to the other 2. That third vector we get by finding the cross product. So I didn't long press long enough. There we go. So this vector here, whatever it is, yeah, that looks terrible. That one is going to be our normal vector n. We just got to figure out what it is. All right. If at some point you have like a solid hour of nothing to do, you've studied for the test, and it's like, all right, I've learned everything there is to learn, and I have all this time on my hands. So basically, nobody has that. But if somehow down the line you found some time on your hands, you could take a look at the video I posted, I believe yesterday, maybe the day before, that explains the derivation of the product. It's really a treat, but it is very lengthy. All right. So what we're going to do is find the cross product between these 2 vectors that I highlighted in blue, which we can call whatever we want. I'm going to call this point P. Yeah, you know what? I'll put the P up here, Q, and then R. At least some semblance of a geometric scheme here. So I need P, which is the first point, Q, which is the third point, and R, which is the second one, right? So I'll just jot those down here. I don't know what possessed me to write those without commas. It's been a long week. So I need vector PQ. All right. Vector PQ or QP, actually we want QP, right? Based off of the diagram that I myself just drew. Kind of going into Space Cadet territory here. All right. So QP, so 3 minus, if we want the components or the displacement vector in component form, 3 minus -1, 1 minus -2, 4 minus -3. So 4, 3, 7 would be QP. Then I also need QR. So let me copy Q. And then jot down R. So I need vector QR. So 2 minus -1, 7 minus -2, and 1 minus -3. All right, because we're pinning them both at Q. So that's displacing the entire array so that Q goes to the origin, so everything else follows along with it. All right, so 3, 9, 4. All right. So then what I need to do is cross up QP with QR to find that normal vector. So N is going to be the cross of QP and QR. All right. So, you know, that takes a little doing, but it's manageable. I was just going to say something, but I decided against it. I don't want to switch gears midstream. So IJK, first vector QP 437, second vector QR 394, so we know there are going to be 2 by 2 square vectors as the coefficients, the scalar coefficients of I, negative J, and K, alternating that way. So that's our next step in the process. 1, 2. Yeah. Highlight a word, it screws everything up. I'll resize all this in a sec just to fit it. Ooh, I'm right at the edge here. And to make that K look a little bit better. So again, to get your individual 2 by 2 square vectors, square matrices, you're going to disregard the row and column that contains each corresponding letter. So the I, get rid of that, so 3794. The J, get rid of that, so 4734. And the K, 4339. All right. And then you could find your determinant any way you want. Diagonal down minus diagonal up is pretty easy when it comes to 2 by 2s. you know, unless you get some funky decimals or other, you know, other types of numbers in there, like irrational numbers, you may then steer away from it. But there's no reason to shy away from doing it by hand here, unless you're just nervous, you know, the kind of experience like I always have where I don't make the mistake except when I have an audience, you know. So like I got to imagine the students' version of that is you never make the mistake, but when you take the test, for some reason, that's the one time you make the mistake. If that's the case, then maybe just pop it in to the Desmos calculator. You know, the default is 2 by 2. You know, it takes a second, but you know, you could have the confidence of knowing that you got your determinant correct. You know, so -51 is I, or is the I coefficient. And again, diagonal down 12. All right, minus diagonal up 63. 12 minus 63, -51. So it checks out. All right. But you could do the same thing repeatedly just to give yourself that peace of mind that you didn't make the mistake, you know. And if you have the app open when you're taking the test, you know, ready to go before you even start the test, then it's even that much easier. So then you look at it and say, okay, well, I thought 16 minus 21 would be -5, and Desmos confirmed it, so I'm feeling pretty confident. So +5j because of the negative coefficient that's already there. And then, you know, you're looking at 36 minus 9, 27, but, you know, again, just in case. And you'll notice how I did determinant of B here because the second matrix is denoted as a B. The added benefit of doing it this way. So if I haven't sold you on it yet, so you get your +27. Oh, that's not a marker. The added bonus of doing it this way is that all of your work is ready to rock and roll. All right. So you can share the calculator. You can just do a screenshot of the calculator itself. You know, like it's your Desmos work. So keep it and use it. You know, like you don't need to do it all on Desmos to then rewrite it. That's why I wasn't putting share links in as the answers on the practice test as a form of laziness. I mean, to some extent, I guess I was putting them in there to demonstrate that those are acceptable ways of representing your answer. Now, some people look at that and say that's not math, and I say I don't care. I don't care what you have an opinion. I have an opinion. My opinion is the one that matters in this case. So if you want to write it all out by hand, by all means, go for it. But if you want to take a screenshot of your Desmos work or create a share link, that's fine too. Right? I think it's just a good use of resources. Aside from the fact that, you know, everybody's trying to combat the cheating, and I'm looking at it like, well, this isn't cheating. So if I let you do it this way, then maybe you won't go looking for another resource somewhere else. You know, like, oh, he's letting us do it this way. Why would we cheat? You know, we got all the different ways we can do it here available to us. All right. So anyway, we got to actually answer the question, which would be, you know, necessary. So that normal vector, since all of these points live on the plane in question, right? The plane contains all three of these points. So I can use any of these points as my fixed point. All right. So it really doesn't make a difference if I want to actually use P. So it's consistent with the formula that we used on the previous page. That's fine, but it really doesn't matter. All we're doing is we're dotting our normal vector against X, Y, Z. So N dotted against X, Y, Z. And we're setting that equal to N dotted against the fixed point. And you choose whichever one you like. It doesn't make a difference. It's all going to come out in the wash. All right. So pick the one you like the most. You know, it doesn't make a difference. All right. So I'll go with Q because that's where I drew my diagram. How about that? All right. I drew my N over there. So -1, -2, -3. All right. So again, our n, I wrote it in IJK notation, but it's really the same in component form, -51, 5, 27. Right. So -51 x plus 5y plus 27z. Then I just want to dot that against the vector -1, -2, -3. Right. So it's represented as a point, but we want the vector. Right. So what we're doing is we're actually dotting it not against the point itself, but against the vector that would originate, for lack of a better term, at the origin, which is the definition of origin, and be orthogonal to the value of n. Right. So yeah, we're just got to carry out that operation. So it would be 51 minus 10 minus another 51, I think. Just in case. So -51 times -1 plus 5 times -2 plus 27 times -3. Oh, -40. Where did I get -10 from? Oh, because 27 times 3 is 81, not 51. I was thinking of 17. All right. So anyway, you get -40 when you dot those two vectors against one another. Just making sure I typed it in all correctly. And the added bonus is that now you have a running account of all the work that you've done to complete this problem. So I think that's perfect because you think of it this way, and I don't think I really need to work too hard to sell people on using things like Desmos to their advantage, but like if just the very act of coming up with the 2x2 square matrices means that you had to have come up with the appropriate QP and QR and recognize that you had to come up with a cross product. So by having that information here, just a little brief description of what you did to get your answer is all you really need. All right. So I think that's a good thing. And I think people are starting to agree with me if they didn't already. All right. So the intersection of planes, and you can check this on GeoGebra if you want, but we're going to just kind of assume that it's right. And if I made a mistake, then somebody's going to find it and earn a typo bonus point for finding that mistake. All right. The intersection of planes, I kind of have this idea in my mind. And unfortunately, the way my mind works is sometimes things make perfect sense to me, but not anybody else. But I look at it as the normal vectors go, so do the planes. So you have that perpendicular relationship. So there is a little bit of a twist on it because they're not parallel to the normal vectors, they're perpendicular. But if there is an intersection between your normal vectors, the lines that include those normal vectors, then there must be an intersection between the planes. If the normal vectors are parallel to one another, then the planes are going to be parallel to one another. All right. So it's kind of a cool little relationship. It's like the enemy of my enemy is my friend. That's that kind of philosophical thing. But if you want to find whether or not two planes are parallel to one another, just determine whether they're parallel vector. I'm sorry, their normal vectors are parallel to one another. Right? It's as simple as that. But sometimes, it's kind of like the old Algebra 1 question, where it's write the equation of the line that passes through this point and is parallel to this line. We're doing the same thing just with the plane. Right, so find the equation of the plane containing the point 314 and parallel to the plane 2x plus y plus z equals 1. So if you identify the normal vector here as 2, 1, 1, the plane containing 314 must also have that same normal vector. So we know what n is. We have that fixed point that we could call P, and so that would correspond with a vector 314. We know the vector Q is our variable vector X, Y, Z. And so just kind of going back to it, it's a matter of dotting N against Q and N against P. All right. So 2x plus 2y, 2x plus 1y plus 1z. So parallel planes will have the same left-hand side, or at least scalar equivalence. The right-hand side is what's going to vary, right? So just like we did before, we multiply, or we're dotting N against P, so we multiply the corresponding parts. So we're looking at 6 plus 1 plus 4. Right-hand side gives you 11. Does it give you 11? Yes. So 2x plus y plus z would be equal to 11. Right. So you're looking at two planes that are parallel to one another. And again, it's all based off the fact that the normal vectors are also parallel to one another. All right. Now, if you actually want to find the intersection of two planes, that's actually kind of fun. It's also pretty easy. Now, when you're dealing with planes intersecting, the intersection will actually form the equation of a line, right? So that's one of the reasons why we talked about the equation of a line in parametric form, because that's how we're going to represent the intersection of planes. And so as it turns out, when three-dimensional surfaces intersect one another, in almost all cases, they trace out some two-dimensional curve, right? But when they trace out a two-dimensional curve in three-dimensional space, we have to represent those parametrically. So, you know, just like in an algebra class, you start off learning about lines, and you get into parabolas, and then you get into other types of functions. That's kind of the same idea here. So we'll start off with lines, and then we'll graduate to other types of functions. Right? So when I'm looking for the intersection between these two planes, there's a couple of ways I can actually do it. One way is very linear algebra heavy. The other way is very algebra heavy. And depending on how you feel about those things, you might gravitate towards one approach as opposed to another, right? So I'll show you both, and then I'll let you decide. Just understanding that there will be circumstances where you're going to want to know or be able to use each method independently of one another. All right. So 2x plus y plus z equal to 1. We got 3x minus 5y plus z is equal to 4. All right, so those are our two equations. We have two equations and three variables. You know, when you're talking about systems of equations, in order to get a fixed value, a fixed solution, you know, just a single coordinate representing the solution, single ordered pair or ordered triple, you would have to have as many equations as you do variables. Not the case here, because what we're expecting is a function to trace out the intersection, not specifically a point. Right? So let's see. I never actually figured out how to mute all, but now it's kind of becoming a distraction. Before it was all right, but now it's kind of like a little much. Let's see. So, oh, there we go. Just had to look for a second. That was easy. All right. So I can solve the system using the elimination method. All right. So right back to algebra 1, just eliminate a variable and go from there. it looks like in this case, it's probably easiest to eliminate the z variable. So I could do that by taking my second equation and multiplying it by -1. Right, so I would have 2x plus y plus z equal to 1, and then -3x plus 5y minus z equals -4. And then I can add the two equations together. Right, if I add the two equations together now, those two variables are going to cancel right away. Right, so we'd be looking at 2x minus 3x is -x. Oh, I'm going to turn off my line draw tool. -x plus 6y equals -3. And so now I can solve for one variable in terms of the other, right? I'm not going to be able to figure out like x equals 2 or y equals 7 or whatever, because I don't have a third equation to help me, kind of triangulate that coordinate answer, but I can get a function that represents that solution. So I can say here, I think it's probably easiest to solve for x. So that's what I'll do. So I'll solve for x in terms of y. So to do that, I can add x to both sides. I can add 3 to both sides. And so I get x equals 3 plus 6y. Right? So I got part of a solution. Right? So then I can kind of take it from scratch here. So back to my original system. And say, all right, well, I was able to get an x in terms of a y. Maybe I can get a z in terms of y. So I can do that by trying to eliminate the x variable. Do angular. Not. All right, so I can multiply my first equation by a -3 and my second equation by a -2. And so I get -6x minus 3y minus 3z is equal to -3. Then I would have, oh, actually, one of them should be positive. Oopsie daisies. 6x, because we want them to cancel, they need to have opposite signs. So plus 10 or minus 10y plus 2z is equal to 8. All right, we want to have consistency in terms of what the equation is in terms of. So since I solved the first one for y in terms of x in terms of y, the only other possibility would be to solve for z in terms of y. So that's what we're trying to do here. All right, so I get -13 y minus z is equal to 5. All right, and solve for z in terms of y, and we'll be on our way to our solution. Right, so here I could just add a z to both sides, subtract a 5, and we would have z equals -13y minus 5. All right. Now, the other issue that we run into here is, okay, so we eliminated the z variable. We eliminated the x variable. If I eliminate the y variable, then I'll never get an equation that represents x in, y in terms of anything else. So the only other possibility is to assume that y is the free variable. Y could be anything. So y is a free variable. All right, a free variable can be anything. So its domain is -infinity to infinity. But what we just assume is that y is equal to y. So therefore, y is equal to some y value without restriction. So we have a relation that gives us y in terms of y, and it's simply that y is y. All right. So now I have three equations, x in terms of y, y in terms of y, and z in terms of y. All right. But if I want to parameterize this, what I would do is I would say, okay, well, my parameter could be something like time, or it could be an angle. There's a lot of things it could be. The typical thing that we use as the variable parameter in parametrics is t. So to make this as consistent as possible with that, what we could say is that we'll let y equal the parameter t. And I can never really judge the amount of space I need to write in a class where I'm supposed to be talking about spatial reasoning. All right, parameter t. So y is equal to parameter t. So therefore, we'd have our system that represents the intersection y equals, x equals 3 plus 6t, y equals t, and z is equal to negative 13 t plus 5. So this kind of goes under the category, because I've met with a lot of confusion over this over the years, where it's like, where the hell did that t come from? And we're kind of looking at it like, well, y could be anything. Y could be equal to elephant, you know? So if that's the case, why not just let it be equal to t and make our life as easy as possible? Because then it's in the appropriate form. I could let y equal 2t. I could let it be equal. I could let y equal alpha. I could let y equal theta. I can let y equal a picture of a smiley face. Right? I can let it be whatever I want, because all it is a value that's representing an unknown. Right? So why not let it be equal to t? You know, if we're working with multiple linear equations like we did before with the intersection, maybe you would subscript it, t sub 1, t sub 2, whatever. But you can let it be whatever you want. Historically, typically we go with t, so why not just be consistent with that? Right? So that's one way to do it. You're not at fault, or you're not some horrible math student if you've looked at this and said,
Professor, real quick, is z supposed to be negative 13y negative 5?
negative 13. Oh yeah, thank you. I had that sinking feeling that I made a mistake. So it was that moment of like, okay, what did I screw up? There it is. Thank you. Everything else is good though, right? Yeah. I appreciate it, because I'm about to show you the next technique. And yeah, and you're not, like I was gonna say, if you don't like this method, that doesn't mean you're a bad math student. You know, like, it's not like you're supposed to love this technique and hate the other one because of the shortcut. It doesn't matter. You might like one as opposed to the other. Just withhold judgment until you see both, right? But good catch on that mistake, because that would have sucked when I like that aha moment at the end where I'm like, look, they're the same, and then they're the not. They're the not. And when I like Starfire from Teen Titans Go. So anyway, so the bottom line is, we want another way to do it because this took a while. All right, so long story short too. So what we can do is take our linear equations, well, they're in the linear form, or the equations of our planes, and strip them down to just their coefficients. All right, so let me just jot it down over here. All right, So we strip it down to just the coefficient. Looks like I lost part of the 4 along the transverse. So let me just grab that back. So we have 2, 1, 1, 1, 3, -5, 1, 4. All right. Now, I'm oversimplifying the process here again because it's not a linear algebra class. There's a lot of theory as to why this works the way it does. The short answer, this part I can tell you, is that this is the result of matrix multiplication. So if I were to take the coefficients 2, 1, 1, 3, -5, 1, and multiply that against the vector x, y, z, using matrix multiplication rules, I should get a result of 1, 4. All right. So what's happening is we're looking at really a linear combination between the vector x, y, z, and also the coefficient matrix to give the solution matrix. Right. But all that does is it just kind of pairs this down to the augmented matrix 2, 1, 1, 1, 3, -5, 1, 4. Right. All of that is a long way of saying that if we pop this into the calculator and ref it, it'll spit back the solution coefficients. All right. So we'd be looking at, and oh, in case you're interested in a little bit more related to matrix multiplication and things like that, I put a couple of videos in the playlist. They're not required. They're right at the very end, but they talk a little bit more about matrix multiplication, like how it works. If you're familiar with Patrick JMT, that YouTube site, it's a good tutorial site. I just put a couple of his videos up there just so, you know, because he gets right to the point, like I sometimes don't most of the time. So anyway, new matrix, 2 by 4, 2, 1, 1, 1, 3, -5, 1, and a 4. And what I do is I ref this bad boy, and I get that disgusting solution. That's all right. Disgusting is okay. I like disgusting. I'm just going to kind of expand it so that you can see the little fraction icon right next to it. That'll convert this disgusting answer into, oh, that's actually not that disgusting at all. All right. So 1, 0, 0, 1, 6 13ths, 1 13th, 9 13ths, and -5 13ths. All right. Now, you may look at this and say, okay, well, I see some numbers that look similar to some of the numbers we came up with before. And this stuff over here, there's some 13s. There's a 6 in there. There's a -5. So it looks like we're on the right track. So it's just a question of interpreting what this matrix is telling us. Well, if the original matrix was born from the coefficients of x, y, z equals whatever the constant was on the right-hand side, then the solution matrix will yield that as a result. All right. So 1x plus 0y plus 6 over 13z equals 9 over 13. And then we'd have 0x plus 1y plus 1 over 13z is equal to -5 over 13. All right. So what we could actually do is represent x and y in terms of z. All right. It's just kind of weird to look at it this way. All right. So I kind of painted myself into a corner. So now I'm scrambling to move some things around. I'll just move this below. All right. Shrink this down a smidgy smidge. and bring it in. All right. So we're looking at x plus 6/13 z equals 9/13, which would be the same as saying x equals 9/13, for quality 13, minus 6/13z. And this one would be the same as saying y plus 1/13z is equal to negative 5/13, which would be the same as saying that y is equal to negative 5/13 plus minus 1/13 z. And again, like same numbers for the most part, but looks a lot different. And that's because they didn't say anything about z being equal to anything. So that tells us that z is the free variable and therefore equal to itself. All right. So we would rewrite this in parametric form where we would say, let z equal the parameter t, in which case we would come up with the solution vector valued function of 9/13 minus 6/13 t. Y would be equal to negative 5/13 minus 1/13 t, where z is equal to t. And yeah, you kind of look at it and say, well, I thought you said they'd be the same. They actually trace out the same curve, in this case, a line, right? The thing is, just like we were talking about with just simply writing the equation of a line, not all t values are the same, right? So the t in this basis is different from the previous t. All right, so we would actually probably subscript this, you know, where you have a T1 in the first case, a T2 in the other case, right? But we could actually change this up so that we could make this look like that. The only thing that we'd have to do in order to make our first, you know, the one that we did algebraically look like the one we did using the matrix would be to set this equal to that to figure out the relationship between the two t's, and then sub in to one equation to make the other. You know, probably more work than you're interested in doing. Most people are fine saying, well, they're equivalent, so we're good, right? Another alternative would have been to go to our, you know, algebraic approach, and instead of eliminating the y variable, you know, because that was actually the easiest one to get rid of, I think. You could have eliminated in the whole process, you could have eliminated the z variable and let that be the free variable, solve for everything in terms of z, and it would have worked out to be the same thing. All right. So it's really entirely up to you how you want to go about doing this, but there's lots of equivalent correct answers that come into play. All right. So when you put these both in the GeoGebra calculator, it plays out, and you'll see it gives you the same graph. All right. Yeah, you know, maybe I'll do that in the video. I'll prove it to you separately because it's kind of beyond what we need to do now, and I think I talked about it enough. All right. In the same vein as what we talked about on the previous page, with distance between, or 2 pages ago, distance between a point and a line. We're going to hop over the distance between a point and a plane because, again, like I said, it kind of fits better later in the course with some other topics. So this is going to get moved to Unit 2 also.
So I'm a little so what is the intersection of these planes?
The intersections are the x, y, and z equations. So
Oh, okay. So what's in purple all the way on the right?
this and this, and or
okay.
that.
All right, thank you.
No problem. All right, so you're always looking for a parametric representation of the intersection, which is going to trace out a curve. All right, so this next little section here, that's going to Unit 2, so we don't have to worry about that. By now, based on the practice test, you already know what's going to be on the test. So you didn't see anything involving distance between a point and a plane, so you know that's not going to be on there. But that's the reason why I thought. All right. So let me actually, so I can chunk the video shorter, stop this recording.